ready to go. Okay, everybody listen. I can hear it. Okay. Let me tell you this. I had nothing to do with this one in a century cold spell and storm in Texas, because some would think that's why I engineered that so we can show how the electrical power distribution throughout the world is important and we cannot live without it. Okay, and it just came in time for me to make a point that how important it is electrification, that Nikola Tesla, the famous inventor from Yugoslavia and who moved at age 25, coincidentally just about age like I moved, so, and changed the world. One thing that was clear is that Texas didn't maintain their networks, didn't weatherize it. So now what happens is the gas pipes froze and they couldn't use to generate electricity. One nuclear out of 4 nuclear power plants went down because of the cold weather. The water pipes, and irony is that they had the fires that they couldn't distinguish, because the fire hydrants also were not working and so on. So the point making is it is very, very important that life, let's say, electricity, electrical utility networks are lifebloods like a blood in humans. And if it stopped working, then nothing works. Okay. Actually, there were in New York, and Vesna will remember or learn about it. There were many blackouts in New York. There was one famous blackout in 1965, and there were many after that. And that 65 blackout, I think the blackout, there were 30 million people in New York, and number of states in the United States, even in Canada, were blacked out for a couple of days. And the thing is, that was a nice blackout, if I can call it. They lost power, they lost lights, people couldn't go to restaurants in evening, so they were stuck like we were now with staying at home. And they said, statistics show that 9 months later, just to the date, there was a sudden spike in new births in New York. Okay, so that's related, it seems like related to that blackout, okay? Okay, so now getting back to this here, I think it is a tribute to Nikola Tesla that in just to put the things in perspective, and I want to put a general introduction so we see where I'm coming from. One of the mysteries is what has historically, who contributed what, and subject of my presentation today is who really invented a transformer. And I'll just give you summary of what you're going to see basically introduced in this lecture and backed it up with some material and documents. It is well known that, and one thing is what we should know just now, that now is 200 years when humanity first time realized connection between electricity and magnetism. It was known 2000 before that there is a magnet that you can that attracts another magnet. So there was magnetism. Electricity came much later, around 1810 or so. Volta come up and developed with Galvani and Volta actually developed a battery to have a continuous source rather than using rubbing and generating the electricity by charges and so on. Anyway, in 1821, it was Ørsted, Danish physicist, who made experiment where he put a DC Volta battery and conducted a DC current and found out, because at that time people used a magnetic needle for a compass to navigate. And he found out, yeah, the current, DC current in a wire causes a force of magnetic needle to orient in particular direction. And then it was Ampere around that time he came with Ampere circuit law, who established a quantitative relationship, how much DC current generates what kind of force on a magnet at certain radius away from this current-carrying, DC current-carrying conductor. And you know what? It's interesting part is that at 1821, Faraday, who was then already at age to participate in the science, he tried, like everybody else, to do the opposite. Say, well, if the constant current, DC current, can generate the force on a magnet, can we have a permanent magnet and generate the constant current in a wire? Of course, this turned out to be impossible goal. And he was trying it like everybody else at the time for 10 years, from 1821 till 1831, to do exactly that. And in the process, he did make DC generators, which turned out to be useless at the time and never really came up to anything. But using his disk and rotating and so on, magnetic disk and mechanical current converting into DC voltage. But in 1831, he came to his famous experiment that he was trying to establish connection between electricity and magnetism and force the constant magnetic force to generate the constant current. He didn't succeed because he, story goes that in a room, he had a very big switch, and he made a transformer, which I'll show you. It is now basically in a Museum of Science and in London, Royal Museum in London, and there's a special room devoted to Faraday. And in Faraday's room, there was a transformer. Really looks like a transformer. It is. It was a big toroidal core with a primary winding, secondary winding. And what did he do? He put on a primary side DC voltage source, and then, of course, when he connect DC source to the primary or transformer, nothing happens, you know. But when he put a switch, and at the moment, then in the next room, he got a galvanometer, which was able to see, even measure, even minute milliamps of the current. And he would switch in one room and go to the other room. By the time he went into the other room, there was nothing. So until one day, he just had his assistant come earlier, and he asked him to turn on the switch while he was in the other room watching a galvanometer. And he noticed that during this transient, the sudden change of the switch is actually causing the change of the current in the output. So this is a birth of his law of electromagnetic induction. You have to have change of the current, which results in the change of the flux, which result in induced voltage on a primary and induced voltage on a secondary. So you could see on the secondary change of voltage. Okay. Now, also at that time, you would be able to use turns on a transformer and use a turns ratio. So if you use a turns ratio of 100 to 1 from primary to secondary, if you use DC source on input and you switch it on and off during on and off period, you would induce the high voltage by a factor of 100 to 1 on a secondary compared to primary. Well, if you wanted to zap someone or kill, you could do that, all right? But it was not sustaining current. It was not continuous. It was not permanent. And in fact, for next 50 years, the whole world gave up on that because they were trying, they considered this alternating current as useless because, let's face it, if you have sinusoidal current, you have positive, it will force the motor to go in one direction, and if you have negative part of sinusoidal current, it will drive the motor in the other direction, which means it won't move. So you needed to rectify it. So everybody was making the generators, DC generator, by rectifying internally generated AC current and AC voltage, rectifying it, and externally shows it as DC voltage and DC current, using complex commutators and mechanical commutators, which are rectifier. Of course, the Tesla was first time in 1882 to some 51 years after Faraday realized that there is two processes happening which are reversible, that every machine could be used as an AC generator as well as AC motor. And you can convert mechanical power into electrical power generators, and therefore, for the first time, you were able to drive the same setup that Faraday has. Transformer with big primary, big secondary, big core of iron, which is magnetic material with high permeability, and you could actually drive it and use it as a source of transmitting higher voltage and so on. It make a continuous periodic drive on it. Of course, in between 1831 until 1882, there were Pixie and some other who actually determined, yeah, you can drive this primary with the alternating voltage, they can generate it, and guess what? Edison light bulb is just a resistor. So you can put on a secondary Edison light bulb and power it for lighting. So there was some effort in between to make a lighting using alternating single phase, of course. But first time when Tesla demonstrated after 1882, in 1893, he demonstrated the first transmission of the power from Niagara Falls, where he had generators and mechanical energy is converted into his synchronous three-phase generators. And then that power from few hundred volts is transferred with a transformer, which are using as a step up to high voltage. Then he had a high voltage three-phase transmission link to Buffalo, which is 26 miles away. Why? Because they needed tens of thousands of current there to convert bauxite into the aluminum with electrolysis. So I need a lot of currents at the volt. And then, of course, there you transform in opposite direction and go from high voltage transmission line down to the low voltage DC. And the point I'm making is in just 10 years, 11, from 1882 till 1893, the first system of electrical distribution was set up. And really, interesting point is, which I think is, so they basically, in 10 years, he already demonstrated, and there's what in Chicago Fair, there was 1895, the big fair, and there was decision made where they're going to use to have all this lighting done using the Edison DC or alternate current, and decision was made alternate current was much better, and therefore the Tesla and Westinghouse got contracts, so they lighted 1895 the fair. Now, another part, interesting part of history is, you know, when is anybody has an idea? Well, you can't talk, but okay, I'll volunteer for you. When was the first Nobel Prize established? Nobel Prizes were established around by Alfred Nobel set up Nobel Prizes in 1896. But it took 5 years before the first Nobel Prize was given in 1901. Why? Because for 5 years, family of Alfred Nobel was, objecting to him leaving the money to others instead of his family, and eventually it was finally went through, and the first Nobel Prize was given in 1901 and the first Nobel Prize was given to invention of X-rays to Röntgen, which is German. The point I'm making is in 1903, there was a Nobel Prize given for physics for discovery of radioactivity, and it was given to Maria Curie. And Maria Curie was, uh, of course, a Polish woman, but she lived in France and worked with Pierre Curie and Becquerel, and three of them were actually got a Nobel Prize for discovery of radioactivity. And funny enough, it's interesting is that she was given a Nobel Prize for her first time. I think I heard someone got a Nobel Prize for their doctorate thesis. So she made a doctorate thesis in December, and Nobel Committee rejected to give her Nobel Prize, but it was her husband, Pierre Curie, and the other fellow who insisted she did all the work, we're just helping. So eventually they gave her Nobel Prize for her PhD thesis, and 2 or 3 years later, she discovered polonium, another element, and got a second Nobel Prize for the discovery. Why I'm making this long introduction is it is shameful for for a Nobel Committee to give Nobel Prize to Röntgen and at the time and other Nobel Prizes, where he already demonstrated a revolutionary system which we use today, some almost 150, 160 years after that. And the only way to transmit a lot of power by speed of light, according to Maxwell. And the other note I would like to say, because they had an opportunity already in 1893, I said 1905, this electrification was demonstrated as revolutionary. So, and Nobel Committee had rule that they can only give a Nobel Prize for those who are living. And a number of very famous people and inventors and others didn't get it because unfortunately they died before they got the Nobel Prize. And the Nobel Committee had until 1943. When Tesla died in January 7, they had opportunity to fix their mistake. And they were watching not only 41 years from 1901, the first Nobel Prize, but they 10 years prior to that, he actually already put the system which we use now today. So in some way, Nobel Prizes are, have to be looked with a grain of salt, finding out who is gaining prizes and for what. And in some way also they started not giving the prizes for a particular invention, but really more like someone did a bunch of work in one area, and it was more like a lifetime award rather than award for particular contribution. Anyway, enough of describing that, but I just wanted to, it's relevant now because we can see we still have, we're still using Tesla alternating system. And one thing that I like in this talk to address is how we can learn a legacy of Faraday and Tesla to see how we can implement it in the present power conversion system, and where present power electronics has one advantage that Tesla and Edison didn't have. We have switches, semiconductor switches, we can switch very fast. We have capacitors, and we have inductors, and we have high frequency transformers. And now for first time after so many years from invention of Faraday invention of electromagnetic law induction, and Tesla's actually contributing, putting the AC system in place. First time we can actually, for first time, consider, can we actually take advantage of high frequency, but not what the people at Tesla and Faraday thought maybe we should generate generators, and Tesla was able to do it, to make a 400 hertz voltage. In fact, on a shipboard is used 400 hertz alternating current is used, and voltage is used to reduce dramatically 10 times size of generators and size of the motors, because they need to be there on a boat where every pound costs. And of course, now we have electrical car, which don't use even 400 hertz. They only use 1.6 kilohertz, believe it or not. and still you can put a 100 horsepower motor in it and to drive the motor with the Tesla with the three-phase variable voltage, variable frequency to drive the motor, and only increase from 60 hertz to 1.6 kilohertz. Yet we are switching now at megahertz, and yet we are not getting a return. Still, we are not. If you say now we are at 60 kilohertz switching compared to 60 hertz, that's 1,000 times higher frequency. And you would think, okay, we could make the sizes of magnetics, the sizes of transformers, 1,000 times smaller. Not so. And we're doing something wrong. And there is a better way around the corner that we should be able to take advantage to indeed make a much smaller size of magnetics and make a not alternating, but high voltage DC transmission line. And now hopefully by the end have a chance to a little bit talk about that as well. Okay.